Hello, my name is Gianna Lee, and this is my Lab 3 report on black holes. Firstly, I will introduce the purpose, explain both computational models, and then provide further understanding. The purpose of this lab is to observe a star's and spaceship's orbit near a black hole. In doing so, we will find the mass of the black hole and the initial velocity needed to escape the black hole via spaceship. This will be modeled computationally. To start, some fundamental principles for this experiment include the momentum principle, the velocity update formula, and the position update formula. The momentum principle is derived from Newton's second law, which states that the total change in momentum with respect to time is equal to dp/dt perpendicular plus dp/d parallel. The velocity update formula is velocity final minus velocity initial plus acceleration times delta t. Through velocity update formula, we also have the position update formula. There are two because with non-constant forces like gravity, we use velocity final instead of velocity average. Moreover, we have the universal gravitational force and its rearrangement to find mass. This principle states that the gravitational force is equal to negative gravitational constant times mass 1 and mass 2, all divided by the distance between the two masses. Some things to note is that the system in part 1 is the star and the system in part 2 is the spaceship. The surrounding is the black hole, and the given mass of the star is 2 times 10 to the 30th power kilograms, and the calculated black hole has a mass of 9.01 times 10 to the 33rd kilograms, and the initial velocity of the spaceship can be 1.55 times 10 to the 7th meters per second. Firstly, in order to find the mass of the black hole, we need to calculate F-net parallel and F-net perpendicular. These are the given variables where delta t is the seconds in a day. Then, using the formulas previously shown, I found the initial and final velocity and position of the star near the black hole. As seen in the line that defines F-net, it is equal to dp/dt because Newton's second law states that the momentum and net force are equal. After running this code, we get the result of F-net, F-net parallel, and F-net perpendicular, and the mass of the black hole, which is 9.01 times 10 to the 33 kilograms. Now in part 2, we need to calculate the net force on the planet and the spaceship to determine how fast the spaceship can be to approach the black hole and not get sucked in. To find the F-net on the planet, I found the gravitational force done by the ship and the black hole. Conversely, to find the F-net on the ship, I found the gravitational force done by the planet and the black hole. This is represented in the code. Finally, applying Newton's second law, we determined the initial velocity needed. After running the code, we can see the trajectory of the planet, the cyan line, and the spaceship, the magenta. Through trial and error, it was determined that the initial velocity of the spaceship can be 1.55 times 10 to the 7th meters per second without getting sucked into the black hole. When observing the two models, one can notice that as the planet gets closer to the black hole, the mass of the black hole increases. One thing to consider, however, is that this simulation is a quote-unquote perfect scenario and only calculates the average mass of the black hole, not the exact initial and final. To further our understanding, here are some probing questions. What is the difference between the net force and its components and the rate of change of momentum and its components? As stated before, there is no difference. Newton's second law states that the net force is equal to the rate of change of momentum over time. Additionally, what initial velocity would my spaceship need to have in order to enter into some kind of orbit instead of just looking at the black hole and leaving? After trial and error, the possible velocity came to be 9.32 times 10 to the 6 meters per second. Thank you for watching.